Hello and welcome to Chaos and Caffeine, episode 22. And if you're watching this on YouTube, please remember to like and subscribe. As a preview of today, we're going to quickly cover the Dunkin' Donuts white chocolate peppermint K-cup coffee, because that's what I had in hand. I've been drinking this all week, so it's not going to be a ooh reaction, but yeah, no, gotta stick with the plan. And then we're going to get into some things having to do with something called the P to F curve. And this is going to go and basically touch on the historical, what it's meant for, and kind of where it's gone. Now, I'm not going to shoot down what marketing folks are. Well, yes, I am. Just kidding. You know I'm going to. So, in any case, we are going to cover the origins of the P to F, what it was actually meant for, and what it's been bastardized into. And unfortunately, I'm part of that. So, I initiated something back in the early 2000s that has then propagated ever since. So it is literally my fault. I checked the history. I'm ground zero or patient zero, whatever you want to call it. So it's my fault. Sorry, folks. It is what it is. So I think I'll insert the apology video here or something, but that's neither here nor there. So in any case, we're going to get into some of that, but first, let's try this out because I really, really want to get into this curve, and I don't want to be 10 minutes in before I finally test the coffee. So I'm trying a new camera and microphone out because we're having some problems with my other one. We'll wait till a screen comes back. There it is. Chaos and the Chaos Engineer Cup. Of course, I'm a Chaos Engineer. Now, to put it to a simple statement, it's not a strong chocolate and it's not a strong peppermint. I do like strong peppermint coffees, however. Normally, this is a medium roast. It's got a nice, just generic holiday taste, so I'm going to stick with that. And then we're going to cover a holiday coffee next week. Haven't decided which one yet and whether or not it'll be an instant or otherwise. Now, it did come up in a comment. I've been sticking with K-cup style stuff. Be perfectly honest, it's software time for me. I've been working with my crew on major updates in our Empower and working along with the crew that works on the Empath software. We've got 2 brand new versions coming out, one of each, that are going to knock everybody's socks off. Let's just say the whole topic of RCM and some of the other stuff will make more sense when we get into the new features, which we will announce between Christmas and New Year as all systems shipping after January 1st of both will have those new software updates. We're going to have for those users that exist now, don't worry, we're not going to charge you for new training. It's a big, major updates, lots of new features in both. All of our users get them for free. That's my commercial. That's what's paying for this, basically. So the Empower and the Empath, and we'll have a quick video in the end. And we have a new saying that goes with all of this stuff. Basically, the motor tells us, we listen, it tells the truth. It'll make more sense when it comes up. And we're going to do things that everybody else has talked about, and we do. So, as I always say, we do what everybody else just talks about. And yes, we dare to do what we're going to do because of over 40 years of my work and work that's gone on in the engineering side and standard side of the industry and investigation and research side of the industry since World War II. And because nobody else has bothered to take it on, not my problem. So in any case, big thumbs up for this coffee. We're 5 minutes in. Let's get into this stuff. So, what was the purpose of the P to F chart? The P to F chart, the original P to F chart, and it wasn't called a P to F chart then, which is why there's some debate on the P to F chart thing. But the first time the chart shows up is in the original Nolan and Heap, and here it is, okay, 410, and you can see it calls it B, so A is standard operation. They're doing this off, by the way, a bathtub curve, and then some type of visible crack. In this case, they're talking about aircraft, and that visible crack happens at B, which that's B, and it's C at some point where you can detect it. So a crack is there, and some inspection would be able to detect it, and then the functional failure is D. So in our world, we'll call this P as the C and F as the functional failure. Now, those who have gone through the class we did on RCM will understand functional failure is defined as the point where the system that you're investigating no longer produces what you need it to produce. Not what's on the nameplate, not whatever else, but what you need to produce. So if I'm looking at a P to F curve of a pump that has to put out, we'll just use one thing, 100 gallons per minute, and it's capable of doing 200 gallons per minute, and I'm testing it, and it's doing 150 gallons per minute, it has not functionally failed until it passes below 100 gallons per minute. That's literally the definition. It doesn't mean it came to a screeching halt. It doesn't mean that an electric motor's bearing has seized unless the motor just not turning at all becomes the thing, right? Functional failure would be, I need the motor to turn at 1785 RPM under full load conditions, and plus or minus whatever percentage, because it's never exact, and it falls outside that range, then there we are. And that would be on a VFD, for instance, or whatever else. So functional failure is the point where the device is not functioning the way you want it to function. Okay, so I've seen some stuff on LinkedIn and everything else saying, oh, you don't need to do this complex RCM. You don't need to do this and that. You can do it really simple, blah, blah, blah. And you can keep it at 100% of what it was supposed to be all the time. Great. If you got the money to do that, do it. But in reality, the idea of the RCM is to do the right maintenance at the right time for the right reasons. And some of those right reasons include whether the equipment's critical or not. Well, if you decide to skip all that and just do it all at once, because this is an exercise I used to do in my RCM classes, it was basically, here's a book from a motor OEM, and come back tomorrow and tell me what it would take to maintain this motor to keep its warranty, and we'll go from there. So people came back in the next day and go, oh my God, that's a lot of work. Yes, it is, because the manufacturer is developing a conservative methodology to extend the life, meaning they're throwing everything at it in order to figure out how to maintain its full capability. Okay, so if I say, oh, well, I got to be careful of this and this and this and this and this, I'm going to do unbelievable amounts of maintenance that are completely unnecessary. And like I said, the company that decides to go in and do it cost effectively and keeps everything within functional failures and does it right is going to have fewer failures, because there is a thing called over maintenance. All right. So in any case, let's get into what the P to F chart really is. And I did an article on this, and I didn't cover all of this on Reliable. So I'll put a link in here somewhere. I'll put it in the thing at the bottom down there, the comments. So in any case, or the description, you guys can put in comments. The whole idea behind the P to F, the original one, okay, so the original concept was to be able to do age exploration. So understanding. It's the hard part of the work. What is the estimated time to failure once things occur? Or, if I have something start, can I detect it? So the original RCM, which by the way goes back to reliability centered maintenance, December 1978. This was commissioned by the U.S. military. Here we go. For the Department of Defense, here is the order asking Stanley Nolan and Howard Heap of United Airlines, who had done the work for the 747, to come up with a title called Reliability Centered Maintenance. This is the original, commissioned by the military, general military, not Navy, not Army, not whatever, in order to come up with a process. This process, there are all kinds. You can still find most of this. Some of us had to save this because it's no longer available in the military libraries. So I have it on a website somewhere. I changed web addresses, so I have to reconnect this, but I'll have a link to it also down below. So you can get a hold of this original RCM book. Okay, it is open, it is public. Okay, so here's the guys. Stanley Nolan was the director, maintenance analysis. Howard Heap was manager, maintenance program planning for United Airlines. Okay, so now we go back to, should be 128. 128. See, there's a lot of stuff in there on how to develop a program. It's actually not that bad a read. 520 pages, not a lot of words on each page. Here we go. So the purpose behind this was that you had a knowable length of time from time studies, from failure studies on equipment. We all have that, right? Well, the good news is that information is available somewhere. For those who are not competitors, this upcoming 22nd of December, I am doing a workshop called Time to Failure Estimation. It's free, several hours. I usually put them down as 3 hours. If it's shorter than that, great. But we're going to be doing it on time to failure estimation, a methodology that I developed in the early 2000s. Well, at least I'm the one who first published it in IEEE, and it talks about how to look and use this type of stuff and estimate time to failure, and 3 different levels, like historical, if you have the history, the best guess based upon the technician who knows the equipment, and then final, the least accurate, is industry wide. Okay, so figure least accurate means about within 7.5%. Now we're talking about a resistance to failure over this period of time. Now, what they very specifically say, both in this, and we're going to cover Mowbray in a second, Mowbray goes far more in depth, defines it as a P to F chart. So technically the name falls to Mowbray under RCM2, which RCM2 was an extension of this thing because he did work also for the military in looking at a more advanced methodology. But for NAVC and NAVAIR, this is the methodology. So Navy, and seeing as, by the way, today is the Army-Navy game, go Navy, and I'm Navy, so I was taught under the 3M program in the 1980s, and this was part of that. So in any case, concept is that whatever inspection has to have some type of predictable point where you can detect it to the time to failure, meaning it doesn't have to be exact, but that resistance to failure has to remain somewhat consistent. Okay, if I don't have consistency, if it goes from, oh, fault, it's done, I really can't use this. Okay, so the whole idea then was they kind of saw it as a point where you had a crack that was visible, but you needed to have an inspection where people would identify it, so the potential failure comes up. So what you want to do between that and the functional failure is half the time between that point and the functional failure. This is a slightly different description. This becomes a different methodology that is talked about under Mowbray, which we're going to cover next. But I need to be able to have an interval where I'm going to catch that. Now, Mowbray's concept, he added in one where I need an interval where not only can I catch that, but I have time to react. So in this case, I might not have a lot of time to react. So there's ways to do that, and that actually falls under the Navier electronics methodology, because electronics, that interval can be much shorter, is I will increase the number of intervals rather than 1/2. It might be 1/3, 1/4, whatever. Okay, so let's take a look at Mowbray. This is his chapter 7. Okay, this I got off of Google Books. I have a copy somewhere. I don't know. I've got to go through. I've still got more boxes of books. I just ran out of shelf space. I believe in paper books. So in any case, so potential failures and on-condition maintenance, meaning you can either through condition-based maintenance or predictive maintenance, and he uses condition-based maintenance in his book. Now, I remember a long time ago, I referred to CBM, and somebody tried to tell me that that was trademarked by this one company, not this company or the company that teaches this stuff, but a tool company, an instrument company, and I found out that was absolute bullshit, meant nothing. So, sorry, I'm going to do Navy. It is Navy Day because Navy's going to win that football game. It is December 13th, and the game starts in a little while, so we're going to get this done pretty quick today. So in any case, so I have potential failures and on-condition maintenance. When I come down here, here's where the P to F is originally comes from. And here's, it says some condition occurring that's predictable, and we'll get into that in a second. Where some failure starts, it doesn't necessarily have to do with age or cycles or anything like that, but something initiates a failure. Well, why did he say that? Because after the original RCM, we knew that the failure modes were pretty much, and the more complex a system is, the more it's a constant potential failure. So the resistance to failure stays at a specific level. There's very little wear out. Components might wear out, but system-wise, right? So like in my Tahoe, my tires will wear out. There's a wear out thing, and there's indicators on the tires to notice that, right? But other components in the vehicle, we know already, because I talked about this the other week, randomly fail, like the electronics, just software. Now, that's going to be next week's topic, the reliability of software. We've been covering a lot in standards, but can I apply this to it? Nope. Nope, I cannot. So in any case, so the idea is the point where you can detect it with some technology, some inspection, some method of periodically checking and seeing something. And this is where things got bastardized because I did it first. And what it was I was pushing electrical signature and motor circuit analysis and current signature back when I was with a company called Alltest. And I used this as a way to pitch that our technology could see things sooner, and I would use specific failure modes. Okay, and that's basically where it went, is all the marketers, vibration, ultrasound, whatever technology came in, and they said, you want our technology because it detects everything the soonest. And, they would, of course, put their technology as the furthest back away. I always found it interesting, though. The vibration and ultrasound guys never include ESA. That's because we are so far to the left on virtually everything they detect as to be ridiculous. And I can laugh at this point, but it's true. So in any case, I mean, we'll detect a change in a bearing at 1 watt or less. No. You're not going to see temperature or hear it until you're at tens of watts. So in any case, I come here and even in the high frequency range. So I come here and uh, I would apply then and say, okay, bearing failure, an electric motor, and bearings, because bearings are wrongly 51% of all failures, because a study in 1983 tells me so. So I'm going to use this chart from that study, which is completely misconstrued and incorrect, and I made the same mistake. I followed people that published that until I got the actual data, because they called them EPRI studies. They were actually IEEE studies that were done. One of them was done, the 1983 one, on large medium voltage motors in power plants, that has somehow been applied to everything. And they said 51% of failure. Now, it had to do with repair reports after a repair was done. So if I take an electric motor and I send it into a repair shop, whether or not there's anything wrong with the motor, and they tear it down and inspect it, what do they do every single time? If I have ball or roller bearings, they replace them. So whether there's anything wrong with the bearing or not, they get replaced. Yep. 1/3 of the motors sent in, according to the study, had nothing wrong with them. So that number is completely skewed. Now, rewind. That I don't just randomly do unless it's called for. And at power plants, especially in that time period, after so many years of operation, say 10 years of operation, if it was a critical machine they pulled out, they would automatically wind it. It was wound whether it needed it or not. Okay? So all the numbers are skewed there. So I redid that as a different presentation based upon the original studies, because there was one every decade. So 1983 had a 1974, had a 1964 to 1954, and then there was a 1995 version that was done on smaller electric machines and metric on offshore platforms, such as oil rigs. So they would, of course, throw in bearings into this and say, because, an electric motor and pump fail, the only reason they possibly could fail is due to bearings. And look, my technology will detect it sooner than their technology. Therefore, you need to buy our product so you can detect bearings, which are less than half of the failures. And you don't have to worry about any of that power quality stuff, electrical discharge stuff, all the other things that drive that bearing failure. You want to do unconditioned tasks to detect a failure, not to mitigate it, but to detect it. I'm going to let that sink in. You are being sold by virtually every technology that the sole purpose of this is to detect a failure, not to fix it, not to mitigate it, not to stop it from failing, but to detect a failure. That's why we see in LinkedIn all of these bearings that are completely destroyed, and everybody points at it, especially all these new investor-owned companies, going, look, we caught this. And we're going, hell, we could have heard that 2 blocks away. But that's neither here nor there. Chances are the actual detection was somebody walking by. Hey, can you check the data? Because, something's not quite right. So, and if you think I'm being derogatory, I'm not. It's an actual case, several of them, as a matter of fact. We've had an exciting year getting mixed up in replacing that technology with ours. So in any case, you have this. Now, what he did is see unconditioned tasks entail checking for potential failures so that action can be taken to prevent the functional failure, not detect the functional failure and allow it to run to that point and go, ooh, we detected it early, but it functionally failed anyways, which is just a different version of reactive maintenance that you spend a lot of money to do on top of the money that you're losing because the damage is done through reactive maintenance, or to avoid the consequences of a functional failure. So it basically allows you to detect and mitigate some condition. It doesn't have to be a bad bearing. It doesn't have to be something. It could be, I've got misalignment. How do I mitigate that misalignment? I have overtension belts. How do I mitigate that so I don't destroy the bearings? Oh my gosh! P to F interval, is the interval between the occurrence of a potential failure and its decay into a functional failure. So it doesn't mean that it's a failure. It means that something is happening. And that an unconditioned task must be carried out at an interval less than the P to F interval. So usually it's half. Now they've got different variations. He introduced something called the net P to F interval, which was basically a way of taking a look so that you would have some time left within this period. Now this goes back to this. You notice that they don't take it all the way up to the functional failure. They take it at some point backwards. Well, what Mowbray did is he went in and described it. So while the original book identifies it and loosely describes it, Mowbray very specifically describes it, labels it. So basically we went from an original concept to an improved concept following the original concept, which is different than what we're doing today. Now I'm seeing all kinds of different names and variations for the stuff that are meant for marketing or consulting. Now this is where he talks about P to F consistency. This is alluded to by Nolan and Heap, but he gets into it, Mowbray does, in this part here, where he talks about the longest P to F interval versus the shortest P to F interval, because I'm dealing with a resistance to failure, okay? So something may occur. It just means, if I have 98%, because you never have 100%. I don't give a damn what everybody tells you. There is no such thing as zero breakdowns. But if I come in there and I say, because there's some equipment you just want to let break down. I mean, everybody's going on about, we need to protect everything. But we covered that in the RCM thing. Criticality is important. There's stuff I just don't need to maintain at all. Let it fail. It's candy. Just toss in something new. That doesn't mean leave it dirty and nasty. I mean, nobody likes working in a dirty, nasty environment. What it does mean is if I have a component that fails periodically and we have a notification that it fails, toss it. I mean, what do you think batteries are in these wireless things, right? So I come here and I take a look at this P to F, and basically if this becomes too inconsistent, then the P to F interval and this type of task doesn't work, okay? And if it happens so often, then, or the time is so short, then I start investigating ways to automatically detect it through, and this has never changed. All these concepts that all this shit that's coming out is brand new is false, okay? I've been dealing with automated detection systems and sensors since I was in the military. We're talking about the 1980s, and it was old then. Okay, this stuff has been around since way back in, all the way back to before Roman times. Okay, so the concept is, that you want some way of detecting something. It could be an inspection, it could be whatever else. For that particular failure mode, for that particular functional failure condition. What are the things that could create that functional failure? And then identify if you can detect it or engineer it out or let it happen. Okay? Scheduled unconditioned tasks are technically feasible if, and this is what he did in addition to the original RCM. Now, these concepts existed in the original RCM, but were not spelled out. The original RCM is 2.5 pages, 3 pages, okay? Or 3.25 pages, sorry, my bad. The Mowbray one is a solid 6 pages just to cover the P to F chart. So technically feasible unconditioned tasks include, it is possible to define a clear potential failure condition. Okay, the P to F interval is reasonably consistent. You notice there's not a fixed anything in there, which makes this timeless, by the way. It is practical to monitor the item at intervals less than the P to F interval. If it isn't, and it's critical, yeah, that's when continuous monitoring becomes a thing. The net P to F interval is long enough to be of some use, in other words, long enough for action to be taken to reduce or eliminate the consequences of the functional failure, giving you enough time to do some kind of mitigation well before the failure occurs. So you take that point of failure, functional failure, you figure out it's 9 months on average, so you kick it back to 6 months, so you do it you do it every 3 months, and then when you detect it, that means you have at least 3 months to plan. So you can build planning around this stuff, folks. I mean, seriously, this is it's important. We've had the instance, and I did this before, where we took a look at a condition on a critical machine in an automotive plant, in an assembly plant. And if that motor failed because it was an environmental device, then they would have been fined hundred some $100,000 per whatever time period. It was, I think it was roughly an hour or something. It was ridiculous. Okay, so they needed to know when we detected a failing bearing in the drive end. We looked at it was with vibration. We looked at it. We also took DSA in order to look at it there and studied it and said, okay. And studying it means we spent an hour on it. Studied a little bit and said, okay. And then management asked the big question: will this survive 6 weeks to the outage, the weekend outage? And so we said there's a risk of failure. It's about, it's a curve. It's a natural log curve. It's an inverse. So inverse of the natural log curve. And we're at about this point now, and it's remaining useful lives. Well, we called it time to failure estimation, but remaining useful life was a thing as well. I'm a data scientist. So we take a look and we say, okay, it's got this, it had this much. Now it's got this much. And from this point to the functional failure, if we go and we calculate out the functional failure from this point of test, and then we go, okay, the natural log of 1 over da 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 gives us, at 600 hours gives us, I'm sorry, 6 weeks. Oh, how many ever? I think we came up with how many ever hours gives us like 28%, or it was a relatively low percentage survival, meaning a high 72% roughly, or 60, whatever it was. It was a high percentage. It was a much lower resistance to failure, basically 28%, 32%, somewhere around there. So we said, why don't we schedule so we have a spare motor brought in, and if we do that within the next week, then we are still at a high resistance to failure. And if something does occur by then we can swap it out. There won't be a lot of damage due to vibration on this motor, so we'll isolate it. And then when that weekend comes up, the motor's already there, we swap it. So we used the on-condition task in order to identify how to correct everything. And basically, that was the P to F curve. The original concept was an inverse natural log to show the resistance to failure over a period of time. These are known formulas, folks. This is not magic. There's reliability engineering behind it. Everybody remembers the reliability formula, right? Well, in this case, what you do is 1 minus the natural log of the time of interest times 1 over the mean time between failure. You know that mean time between failure thing everybody's telling you is useless? Well, it's because they don't know fuck all about reliability. And I don't give a shit. Sorry, folks, and I'm sorry if I've insulted any. No, I'm not. Some of the crap that's being put out now about, oh, this is no good and that's no good, leaves out the history and the work that was done in the past. And you must come to them because they're the only ones who know their new magic formulas that have not been tried, tested, or anything else other than maybe something they got out of an academic paper. But if you start looking at the researchers, especially in areas in physics, the pushback on what's going on in that side is incredible. Where they're saying that most of the stuff happening now, including in reliability engineering, is becoming pseudoscience. So you're going to see our stuff coming out hard, old-fashioned, back to basics, giving the answers everybody's asking for. That everybody, all the new folks are saying, oh, no, it's squishy. We can't really tell you anything because we don't know what we're talking about. We just develop, so, oh, no, we don't even develop the software. We have somebody in another country develop software, and we even say to now that somehow, amazingly, I love this one because I just saw it the other day, like yesterday. Amazingly, oh my gosh, we don't need to use cloud systems like AWS and all the other guys in order to do machine learning and AI. Um, we can do it on individual computer. I've been doing it for decades. All of our systems do it now. This is some new invention? I'm sorry, folks. A lot of the crap out there is exactly that. But neither here nor there. Understand the P to F curve, what it's really for, then you can take a look at your existing technologies. You can take a look at your existing stuff. You can take a look at your actual failure modes for your equipment, and you can determine then how to use the technologies you have. How to use, or if you want to adopt a new technology, figure out what failure modes it detects. Does that make sense for your applications? Do you have a history of those types of failures? Okay, before you even get into RCM, somebody comes along and says, our stuff does great. Look at the P to F curve for direct drive fans, and you don't have any direct drive fans? Then what is that telling you? It's telling you absolutely crap all. So with that, like and subscribe, folks. Next week's going to be even more exciting because we're hitting the end of the year, and I'm getting frisky. I'm sitting here doing software and occasional field jobs because, well, we're putting everybody off till January where we can because we got big things coming and I'm part of the process. So that makes me a little frisky and annoyed. Staring at computer screens, not as much fun as playing with the toys. So with that, have a great day. Remember to follow Relia Squatch, follow Motor Doc, and you'll see more of this stuff. Thank you very much.